Well, hello and welcome to our first Tuesday lecture via video, I think. Anyway, this is going to be a regular thing until such time as COVID vaccines become available in the area again. So this will proceed pretty much as it has on Thursdays. And I'll just continue where we left off last Thursday, which was with nomenclature. We had gone over the idea of ionic compounds and molecular compounds. Remember, ionic compounds are compounds where basically the compound will involve a metal and a non-metal together, like sodium chloride, or say a metal and a polyatomic ion, like sodium nitrate, or maybe in a few cases, even just polyatomic ions with no metals present at all, like, for instance, ammonium nitrate. Ionic compounds form because because they involve positive and negative ions, which being opposite in charge are attracted to each other, and that attraction of the positive and negative ions for each other is known as an ionic bond. Ionic compounds exist as a three-dimensional array of repeating positive and negative ions. They alternate positive, negative in 3 dimensions. And when we write the molecular formula for an ionic compound, we normally write the lowest whole number ratio of the ions to each other, with the positive ion first and the negative ion second. Molecular or covalently bonded compounds are compounds that are made up entirely of nonmetals and no polyatomic ions are present. And they form by sharing electrons. When you get two nonmetals together, like say hydrogen and oxygen and water, generally one of those elements will have a stronger attraction for electrons than the other one does, but there's not enough of a difference for one of them to actually take the electrons right away from the other one. So in this case, oxygen has a stronger attraction for electrons than hydrogen does, but not strong enough to take the electrons right away from the hydrogen. So the hydrogen and oxygens end up sharing the electrons. That sharing is known as a covalent bond, and it results in compounds that are known as covalent type compounds or molecular compounds, because they exist as separate independent little units known as molecules. And so H2O, water, consists of a bunch of little molecules, each of which has 2 hydrogen atoms and 1 oxygen atom. And those molecules, each of those molecules is unconnected to any other molecule. Okay, so there's separate independent little units known as molecules. And that's a bit of a review. Where we actually left off was with nomenclature. Nomenclature is just a fancy name for naming compounds. And in naming compounds, there are actually several different ways to name compounds. A lot of compounds, especially ones that have been known for a long time, will often be known by common names, which don't really follow any set of rules, like water for H2O. But because there are literally tens of millions of compounds out there that are known, and probably millions and millions more yet to be synthesized, there has to be some sort of systematic way of naming compounds, just to keep from getting confused. You can't give everything a name that just sort of comes out of the blue and is unrelated to anything else, like water for H2O. You can't do that with everything, because if you do, that's going to be like tens of millions of different names that you would have to try to memorize. And that's a fool's errand. If we use a set of rules for naming compounds, then it becomes much easier to tell what is present in a compound just from its name. So if you use systematic rules for naming compounds, then you should be able to write the formula for a compound from its name, or the name of a compound from its formula. And that makes communications between scientists much easier. The system for naming that we use was one developed by the International Union of Pure and Applied Chemistry, otherwise known as UPEC. And they lay out a certain series of steps for naming compounds. First of all, depending on what type of compound it is. So there are actually different rules for naming compounds depending on whether they're ionic compounds or molecular or covalent type compounds. Starting with the IUPAC rules. With binary compounds, those would be the simplest example. Binary compounds are compounds that just contain two elements, binary as in two. Binary compounds can be ionic or molecular. Water, H2O, is a molecular type compound, and it involves hydrogen and oxygen, so that's bimolecular. But, and where is it up here? I saw it somewhere. Maybe I didn't. Sodium chloride involves the metal sodium and the, oh, there it is right there. Sodium chloride involves the metal sodium and the nonmetal chloride, which makes it an ionic type compound. But that's also binary because it involves sodium and chlorine, two elements and nothing else. Okay, so for ionic compounds, let's start with the rules for ionic compounds. Not yet. For ionic compounds, with binary ionic compounds, using monatomic ions, that is compounds like sodium chloride, where the positive and negative ions are derived from a single atom of the element. That, in other words, not polyatomic ions yet. We'll get to those in a minute. That would mean that there are only two elements present if it's a binary compound with monatomic ions only. The name of the compound will just be the name of the cation, which we normally write first in the formula anyway. And the name of the cation will be just the name of the metal, followed by the name of the anion, which we normally write second. So cation first, anion second, and it goes like that for the formula and for the name. There's a table on page 106 that you can look at that lists out a bunch of examples, and I'll just include a couple here. If you have the binary ionic compound made up of sodium ions and chloride ions, then that would be known as sodium chloride. If you have the binary ionic compound made up of calcium ions and bromide ions, that would be calcium bromide. And the fact that NaCl has only one ion of the cation and anion, and the fact that calcium bromide is CaBr2 is really beside the point. That's something that you can figure out based on knowing the charges on the cation and anion. So if I say sodium chloride, you know that the formula must be NaCl, because Na is the symbol for sodium and Cl is the symbol for chloride, and Na is +1 and Cl is -1, so they go together in a 1-to-1 ratio, hence NaCl. If I say calcium bromide, then you know that calcium is involved and bromine or bromide ions are involved. And you can figure out that it's CaBr2 because calcium ions are in group 2A of the periodic table, so they always form ions with a +2 charge. And the bromine is in group 7, and it's a nonmetal, so the charge on its ions will be group number -8. That's 7 - 8, which is -1. And it takes two -1s to cancel out a single +2. So it's got to be CaBr2. Okay, so that's how you can go about finding the formula from the name. Of course, some ionic compounds involve polyatomic ions. And because of this, it is important that you at least learn to recognize polyatomic ions when you see them. Since our exams are going to be open book, you don't have to memorize the names and the charges on polyatomic ions. You can look those up. There's a table in the textbook, they're in Wikipedia, and a bunch of other places. But it's still good to be able to recognize them, because if there's a polyatomic ion present, it needs to be named as the polyatomic ion, not and should not be named according to the individual elements in the polyatomic ion. And of course, there are a few cases here where a compound can exist of nothing but polyatomic ions, and there won't be any metals present to tip you off that it's an ionic compound. Okay, so just you learn to recognize the polyatomic ions when you see them. The name takes the same form as before, cation first, then anion, and the name is simply the name of the cation followed by the name of the anion. So if we have NaNO3, that would be a sodium ion combined with a nitrate ion, so the name would be sodium nitrate. And recognizing NO3 as the nitrate polyatomic ion is important, because otherwise you might try to name this as something like sodium mononitrogen trioxide or something like that. And that's not what it is at all. This is sodium nitrate. Sorry, excuse me. I found when I was first learning about polyatomic ions, it helped me if I were to write the polyatomic ions in parentheses whenever I saw them. So you could also write sodium nitrate as Na parenthesis NO3 close parenthesis, and that's not wrong. We don't normally use parentheses around the polyatomic ion unless there is more than one of the polyatomic ion in the formula, but it's not wrong if you do use parentheses even when there's only one. So you can do that, and it can help you kind of remember that's a polyatomic ion. I need to name it as a polyatomic ion, and also the polyatomic ion reacts as a unit, and it tends to remain intact during chemical reactions. Those are also important things about polyatomic ions. You can tell that the formula for sodium nitrate has to be NaNO3 because sodium is in group 1A, so its ions will always have a charge of +1. And the nitrate ion, if you remember or look it up, has a charge of -1, so it will go together with sodium in a 1-to-1 ratio. On the other hand, if you have a compound that consists of aluminum ions and sulfate ions, that compound would be known as aluminum sulfate. Okay, we use parentheses around the SO4 in this formula because there are 3 of them in the compound, and along with 2 aluminum ions. And you can figure out what the formula should be by just laying it out like this. We know that aluminum ions, or aluminum is in group 3A, so its ions will have a charge of +3. And we know that the sulfate ion, if you either remember it or look it up, has a charge of -2. And the only way to get those to go together so that the charges will cancel out would be basically to cross multiply. The charge on one ion becomes the coefficient for the other one. So 2 goes here and 3 goes here, and those coefficients become subscripts when you put them together in the overall formula for the compound. So it's Al2SO4 3. 2 ALs with a +3 charge each gives you a total positive charge of +6, and then 3 SO4s with a -2 charge each gives you a total negative charge of -6. So +6 -6 balances out to no charge overall, and that's why the formula has to be Al2SO4 3. You could have, say, a compound that consists of the ammonium ion and a chloride ion, and that would obviously be called ammonium chloride. You could write the ammonium ion in parentheses if you like. It wouldn't be wrong, but we usually don't do it that way because there's only one of them in this formula. The ammonium ion has a charge of +1, and chloride ions, being in group 7A of the periodic table, will have a charge of -1, so ammonium and chloride will go together in a 1-to-1 ratio, NH4Cl. Notice there are no metals present in this compound, so you have to recognize that NH4 is a polyatomic ion in order to realize that this is an ionic compound and should be named according to ionic compound rules. Another example would be if there are 2 polyatomic ions involved. That is possible. So if you have a compound that involves the ammonium ion and the sulfate ion, the name would be ammonium sulfate. How many of the ions are present in the formula for the compound doesn't really matter for the name. It's just ammonium sulfate. It doesn't matter that there are 2 ammonium ions and 1 sulfate. You can figure that out from the charges on the ions if you need to. The name is just ammonium sulfate. We put parentheses around the ammonium because there are 2 of them in the compound, in the formula for the compound, but there's only 1 sulfate ion, so we normally wouldn't put parentheses around that. But if you wanted to, I would not mark it wrong. So that's okay also. And remember, the fact that there are 2 ammonium ions in each formula unit of this compound means that in total, there are 2 nitrogen atoms, because there's 1 nitrogen atom for each ammonium ion, but there are 2 ammonium ions. So that's 2 nitrogen atoms total, 8 hydrogen atoms total, because there are 4 hydrogen atoms for each ammonium ion, but there are 2 ammonium ions. So that's 8 hydrogens total, and then 1 sulfur and 4 oxygens, because there's only 1 sulfate ion present. The ammonium ion has a charge of +1, and the sulfate ion has a charge of -2. So obviously it's going to take 2 ammonium ions to cancel out the charge on 1 sulfate ion, hence NH4,2SO4. A bit of a curveball arrives when we are dealing with ionic compounds that involve transition or B group metals. The catch about the transition metals is that most of them can take more than 1 charge in compounds. Like for instance, there are a lot of copper compounds in which copper has a charge of +1, but there are also a lot of copper compounds where copper has a charge of +2. There are a lot of iron compounds where iron has a charge of +2, but there are also a lot of iron compounds where it has a charge of +3. Some of the transition elements can actually take quite a few different charges. So chromium can be +1, +2, +3, +4, +5, or +6, with the ones underlined, the 2, 3, and 6 being the most common. Manganese can be +2, +4, or +7. All of those are quite common. And so in naming the compounds that involve these ions, that is transition or B group metal ions, we have to supplement the normal naming system for ionic compounds in order to indicate what charge the ion has on it in that compound. Because for instance, with copper, you can't just, if you have say a compound that contains copper ions and chloride ions, you can't just call that copper chloride, because there's also this, which contains copper ions and chloride ions. And so if you call this copper chloride, what's that? Well, that's copper chloride too. Also, I mean, copper chloride also. So we have to have a way of distinguishing one from the other. And IUPAC, in its infinite wisdom, has decreed that the way to distinguish these compounds from each other would be to specify the charge on the metal ion in each of them. Now, remember, you only have to do that for transition metals. The metals in the B groups are the lower line groups in the middle of the periodic table. These guys here and these guys down here. So if you've got like sodium or calcium, or aluminum, you don't have to specify the charge because they're in the main group main groups of the periodic table, and they can only take 1 single charge, which is their group number. But the transition elements, their charges do not necessarily correspond to their group number, and most of them can take more than 1 charge anyway. So it's the transition elements where you have to specify the charge. The way that you specify the charge, well, actually, let me get to that in a moment. I'll go over what we got here first. First of all, before you can specify the charge, you have to find out what the charge is on the metal ion in the compound. So for instance, if you have CuCl, you start with what you know. You know, first of all, if this is the formula for a compound, it must have 0 charge overall. And we also know that chlorine ions are found in group 7A. They're nonmetals, so their charge must be 7 - 8, which is -1. So chloride ions always have a charge of -1. And if it takes only 1 copper ion to cancel out that -1 charge on the chlorine, then the copper must be +1. Okay, so what we've got here in CuCl is copper +1, or just plus, copper plus. In copper chloride with CuCl2 as the formula, we know again, being a compound, the total charge on that formula must be 0. And again, we know that chloride ions always have a charge of -1. And this time, if it takes 2 -1s to cancel out the charge on the copper ion, then the copper ion must have a +2 charge in that compound. So CuCl involves copper +1, CuCl2 involves copper +2. In most ionic compounds, you can also do the reverse of cross multiplying, but that doesn't always work, so I'm gonna skip over that. The name of the cation then would be the name of the metal followed by a Roman numeral in parentheses indicating the charge. And what that means is that since CuCl contains copper, excuse me a moment, with a +1 charge, the name of that compound would be copper 1 chloride. The 1 in parentheses indicating the charge on the copper. It's important to remember that because when we get into naming covalent type compounds, we're going to be using numbers that actually give you the number of atoms rather than the charge. So it's important to keep straight that the numbers involved in naming ionic compounds refer to the charge on the cation. Okay, and you only use those numbers if the cation is one of the transition metals. And we already saw up above that CuCl2 contains copper with a +2 charge, so this would be known as copper 2 chloride. If we had iron chloride with a formula of FeCl2, we would find that the iron in that compound has a charge of +2. So FeCl2 is actually known as iron 2 chloride. And FeCl3 involves iron +3, which would be named iron 3 chloride. Okay, dealing with some ions that don't have charges of + or -1. CrO, chromium oxide, if you work this out, we know that the overall formula must have a charge of 0. Oxygen is in group 6A of the periodic table, meaning that it's a charge of its ions would be 6 - 8 or -2. And if chromium pairs with that on a 1-to-1 basis, in other words, it only takes 1 chromium to counteract or wipe out the -2 charge, then chromium must be +2. This would be called chromium 2 oxide. Cr2O3 is also a chromium oxide. And if you work this out, again, assuming that the overall formula must have 0 charge, and again, knowing that oxygen in ionic compounds always has a charge of -2 because it's in group 6, and 6 - 8 is -2. The 3 oxygens collectively would have a charge of -6 because 3 times -2. In order to bring that total charge back up to 0 for the overall compound, that would mean that the chromiums must have a collective charge of +6. But there are 2 of them, and they share that +6 charge equally. So each chromium must be +3. And that would be called chromium 3 oxide. There is yet another common chromium oxide that has the formula CrO3. And if you work that out, you find that chromium has a charge of +6 in this compound. And that would be called chromium 6 oxide. Okay. Chromium 6 oxide. Some ionic compounds are known as hydrides. That is, when a metal combines with hydrogen, the hydrogen actually has a negative charge and the metal will have the positive charge. And the name of the compound is simply the name of the metal ion followed by the word hydride. Okay, so the formula would be the metal cation followed by H or H's, depending on how many it takes. The name is just the name of the cation followed by hydride. So NaH would be sodium hydride, CaH2, and the charge on the hydrogen is -1. So if you're going to combine it with calcium, it would take 2 of the -1s to counteract the +2 charge on the calcium, because calcium is in group 2A of the periodic table. And AlH3 would be aluminum hydride. You could also have transition metal hydrides. So you would, in those cases, you would have to specify the charge on the metal ion. So like, for instance, CuH would be copper 1 hydride. CuH2 would be copper 2 hydride. And so on. They're not terribly commonly encountered in general chemistry, so I'm not going to spend a lot of time on it. And next, though, ionic hydrates. Hydrates refer to water. Sorry. And hydrogen, in fact, got its name from the fact that it's involved in water. Hydro is the Greek word for water. Ionic compounds to which water molecules are physically attracted are known as hydrates. And so for certain ionic compounds, in an environment that isn't excessively dry, they will have a certain number of H2O molecules that are just sort of physically clinging to the matrix of the positive and negative ions. So there are little water molecules interspersed in that matrix. And it turns out that for most of these hydrated ionic compounds, the number of water molecules is predictable, and it can be related in a definite way to the formula for the compound. Sorry, excuse me. The attraction of the H2Os for the ionic compound is merely a physical attraction. The water molecules are not chemically bonded to the positive or negative ions of the compound. And the presence of those waters of hydration, as they're known, can change some of the physical properties of the compound, but not the chemical properties. So like the same compound with different numbers of waters of hydration present can actually be different colors, for one thing. But it will still react the same way in chemical reactions. Some compounds can have more than one number of waters of hydration. And the waters of hydration can vary from one compound to another, but also from one molecule to another for the same compound. And so because of that, the waters of hydration have to be included in the formula and in the name. And as I said, the waters of hydration for these types of compounds will be present unless the environment is very hot and or very dry. The water, because it's just a physical attraction between the H2Os and the rest of the compound, those waters of hydration can be driven away relatively easily, like by heating, for instance. And in a lot of cases, you don't really even have to heat it very much. And the waters of hydration will basically turn to steam and go off into the air. And the rest of the compound will remain behind because ionic compounds have very, very high melting and boiling points. But once you stop heating it, unless you put the compound into a very dry environment, those waters of hydration will gradually come back. And they will originally reach the same number that were there originally. Or you can put them back just by pouring some water over the compound, and they'll come back immediately. Once the waters of hydration are gone, the compound is known as anhydrous. A or an is a prefix in Greek that means not or without. And so anhydrous would mean without water. So anhydrous means that you've driven all the waters of hydration away and you've just got the ionic compound left. The way that you name ionic compounds with waters of hydration would be just the name of the compound, followed by a Greek prefix giving the numbers of H2Os, and then the word hydrate. The prefixes are based on the Greek words for numbers. So mono would mean that there's only one H2O attached to each formula unit of the compound. Di would mean that there are two H2Os for each formula unit of the compound. Tri would mean 3, tetra would mean 4. You think of geometry for some of these names. Penta, as in pentagon, would mean 5. Hexa, as in hexagon, would mean 6. Hepta would mean 7. Octa would be 8. Nona would be 9. And deca would be 10. So for instance, CuSO4.5H2O. Pretty blue substance, sort of blue crystals, a nice royal blue color, kind of probably about the color of a blue Sharpie, actually. And the name would be first the name of the ionic compound, CuSO4, which is copper 2 sulfate. Because remember, the sulfate ion has a -2 charge. So if it goes together with copper on a 1-to-1 ratio, that would imply that the copper must be +2. So copper 2 sulfate, and 5 H2Os would be pentahydrate. It kind of blotted there, so I wrote penta above it again. So pentahydrate, copper 2 sulfate pentahydrate. If you were to heat this substance, the pretty blue crystals would gradually turn into a white powder, and you would have CuSO4, which is anhydrous copper sulfate. If you then let the anhydrous copper sulfate just sit out on the counter for a while, especially if it's a humid day, it will eventually gradually start turning blue again, and you will restore the 5 H2Os. So that is sort of a characteristic number. CuSO4 characteristically has 5 H2Os attached to it, unless the environment is really hot or really dry. Another one would be MgSO4.7H2O. This is better known as Epsom salts. The first part of the compound would be MgSO4. That's magnesium sulfate. Because magnesium is one of the main group metals, you don't need a Roman numeral. So it's magnesium sulfate. And then 7 H2Os would be heptahydrate. And then another one would be FeCl3.2H2O. The dot here is what we use to represent the physical attraction between the waters and the rest of the molecule. We didn't want to just write 5H2O or the H2Os after the formula for the compound, because that would imply that there's a chemical bond there, and it's not a chemical bond. So the dot represents the physical attraction. FeCl3.2H2O would be iron 3 chloride dihydrate. Okay, 2 H2Os. Okay, before we get into naming of covalent type compounds, I notice we're fairly well over the limit for the first segment, so I'm going to stop there and we'll pick this up in part B.